one of the leading physicists of today, renowned for his significant achievements in the realm of physics, has shared his thoughts on a groundbreaking discovery. Michio Kaku, acclaimed for his remarkable contributions to scientific progress, has recently affirmed that the James Webb Space Telescope has uncovered 6 enormous galaxies that scientists previously thought were impossible. These findings could potentially open new frontiers in our comprehension of the universe. The discovery is thrilling and transformative, challenging prevailing theories regarding the formation and evolution of galaxies. Therefore, these developments are undoubtedly worth closely observing. The confirmation by such a prominent scientist as Kaku highlights the importance of these revelations. Kaku, a physicist of both American and Japanese descent, is recognized as an authority in classical experimental physics as well as quantum mechanics. Unlike other more traditional and skeptical scientists, Kaku remains open-minded and has embraced the astonishing results from the James Webb Space Telescope mission. His willingness to accept new discoveries and share them with the public underscores his dedication to advancing our understanding of the cosmos. We are pleased that this distinguished scientist has chosen to speak out and publicly share these undeniable findings. Kaku's enthusiasm, often with a tone of amused wonder, is evident in his remarks on the findings of the James Webb Space Telescope. He expressed that this discovery has been a significant moment that has captured his attention. Join us as we explore the implications of Kaku's groundbreaking analysis of these 6 massive galaxies. Kaku is a scientist who has always shown a willingness to consider fresh theories. Throughout his career, he has embraced ideas that challenge established norms, recognizing that Einstein's equations of relativity and Newton's laws, while fundamental, are inadequate to fully explain the complexity of the universe. Kaku acknowledges that the discovery of these new galaxies could greatly enhance the scientific field. While many of his colleagues have been reluctant to adopt this perspective, it has raised concerns among advocates of the Big Bang Theory and opponents of quantum mechanics. However, Kaku finds such concerns laughable. The James Webb Space Telescope has revealed the existence of 6 massive galaxies dating back to the earliest days of the universe, each of which contains more stars than our own Milky Way, even though they formed only 200 to 700 million years after the Big Bang. The astronomers responsible for this discovery have labeled these galaxies universe breakers, because, if confirmed, they would dramatically reshape our understanding of the cosmos. The significance of these findings is profound, suggesting that the early universe was far more dynamic and complex than previously imagined. Something doesn't align anymore. The Big Bang Theory tells us that the universe was a chaotic, high-energy state right after the event. Solid structures took hundreds of thousands of years to form, and it took millions of years more for these objects to accumulate enough density and begin emitting light. The creation of complex structures like galaxies was believed to occur much later. Some of the newly discovered galaxies surpass the Milky Way in size, and their intense luminosity suggests they were likely producing hundreds of new stars annually, compared to the sporadic star formation in our galaxy. The precise timing of the formation of the first galaxies remains uncertain, though it is clear that initially, the cosmos may have consisted only of isolated stars or small groups of stars that eventually merged to form larger, more substantial accretions. These dwarf galaxies would have collided with others, growing over time. According to traditional theories, large, organized galaxies could not have existed at such an early stage, which leads to the question of whether the universe is far older than previously thought, or if sophisticated galactic formations emerged earlier than anticipated. This possibility challenges conservative scientific views, which still struggle with the model. Some branches of physics outright reject these findings, questioning the accuracy of the age estimates. Kaku acknowledges this skepticism, noting that many old and incorrect theories have persisted due to the prestige of certain scientists, and it was only through pivotal experiments that these outdated ideas were debunked. He emphasizes that the true foundation of any science, particularly physics, lies in the work of experimentalists who keep theorists in check. In fact, our understanding of the universe's origins is still very limited. Kaku's quote highlights the need for ongoing experimentation and validation in scientific inquiry. The Big Bang Theory was established in 1927 after observations of the universe's expansion, leading to the conclusion that the cosmos originated from a single, infinitely dense point and has been expanding ever since. At the time, the notion of a universe with a clear beginning and an end was difficult for people to grasp. The idea of an infinite universe, without a beginning or an end, was beyond human comprehension. Even today, scientists still grapple with this concept, but it is crucial to reassess these possibilities. These new findings do not fit within the framework of the Big Bang Theory, but science has continually shown that re-evaluating and remaining open to new ideas is essential to the scientific process, just as confirming theories through empirical evidence is necessary. When Einstein was young, it was widely accepted that stars and planets were fixed in their positions within the universe. However, today we know that everything in space is in constant motion. Planets orbit stars, stars move within galaxies at speeds of hundreds of kilometers per second, and entire galaxies themselves travel rapidly through the cosmos, with their future movements still uncertain. This dynamic view of the universe challenges long-held assumptions and reinforces the need for continued exploration and adaptation in scientific thought. Today, scientists face the challenge of accepting uncomfortable truths and realizing that theories are not absolute until they are rigorously tested and confirmed by direct observation. The Big Bang Theory emerged from the realization that galaxies are receding from each other, with the distance between them correlating to their separation from Earth. This observation, known as Hubble's law, led to the conclusion that the universe is expanding. Over time, evidence like cosmic background radiation and the redshift of light from distant galaxies seem to support this theory. However, it is essential to remember that in the past, people once believed the Earth was flat and that the Sun revolved around us, also supported by apparent physical evidence, until advancements in technology and discoveries painted a clearer picture. We are now witnessing a similar situation. The James Webb Space Telescope was expected to confirm assumptions related to the Big Bang Theory, but instead, it revealed these 6 galaxies, which seemed improbable. This discovery serves as a reminder that science is always evolving, and scientists must be willing to embrace new findings and reconsider existing models in light of new evidence. The unexpected discovery challenges established understandings and calls for a reassessment of long-standing cosmological theories. Researchers use redshift as a tool to determine certain properties in the study of the universe. Redshift, also known as the Doppler effect, describes how light shifts in color as the source and observer move relative to one another. To illustrate, imagine standing still and hearing a car's engine grow louder as it approaches. Once the car passes, the engine's sound changes because the sound wave frequencies are altered. The same principle applies to light. As a distant star approaches us, its light shifts toward the blue end of the spectrum. As it moves away, the light shifts toward the red end. This phenomenon, called redshift, has been used by physicists to calculate velocities and distances in cosmic measurements. However, small errors in these measurements can have significant implications. The methods previously used for these measurements are now under review, and it will be interesting to see the results of these new investigations. As we explore the latest findings regarding the universe, it is essential to question whether they are due to errors in redshift data or whether some scientists are simply rejecting the evidence. This ongoing scrutiny of measurement techniques underscores the evolving nature of scientific inquiry. Thank you for watching this video. As always, feel free to post any questions in the comments section. If you found Michio Kaku's analysis interesting, be sure to like, share, and subscribe to the channel so that more people can explore these topics. Stay tuned for more updates, and thank you once again for watching. This call to action encourages viewers to engage with the content, fostering a community of inquisitive minds eager to explore and comprehend the latest scientific discoveries. The study of our vast and intricate universe continues to captivate and challenge scientists worldwide. From early cosmic theories to recent breakthroughs made possible by cutting-edge technology, each discovery reshapes our understanding and pushes the boundaries of human knowledge. One of the most profound and ongoing questions in cosmology pertains to the origin and evolution of galaxies. Galaxies, which are cosmic cities composed of stars, gas, dust, and dark matter, are held together by gravity. Understanding the formation and evolution of galaxies is crucial not only for unraveling the mysteries of our universe, but also for confirming or challenging established theories like the Big Bang Theory. The Big Bang Theory, proposed nearly a century ago, suggests that the universe began as an infinitely dense point and has been expanding ever since. This theory emerged from the observation of the universe's expansion and the cosmic microwave background radiation, considered the residual heat and light from the early universe. However, recent discoveries, particularly those from the James Webb Space Telescope, have raised questions about the core assumptions of the Big Bang Theory. The telescope, with its unmatched sensitivity and resolution, has detected galaxies that defy conventional understanding. These galaxies, which date back to just a few 100 million years after the Big Bang, are unexpectedly massive and luminous, suggesting that the early universe was much more dynamic than previously thought. These findings have significant implications. They prompt scientists to reconsider the timeline and mechanisms of galaxy formation. The discovery of galaxies that were already so evolved shortly after the Big Bang challenges the idea that galaxies formed gradually over billions of years. Additionally, the James Webb Space Telescope's observations reveal the complexity of galactic evolution, showing that galaxies could rapidly grow and experience significant star formation early in their histories. This new evidence forces astrophysicists to revisit their theories on the interactions between stars, gas, and dark matter during the early universe, which may have led to the formation of the first galaxies. Beyond transforming our understanding of galaxy formation, these discoveries highlight the essential role of technological advancements in pushing the boundaries of astrophysical research. With its infrared capabilities, the James Webb Space Telescope allows scientists to peer deeper into space and further back in time than ever before. By analyzing the light emitted by distant galaxies, astronomers can reconstruct their histories and uncover clues about the conditions that prevailed during the universe's formative years. Redshift, a critical tool in cosmological research, plays an essential role in these investigations. Redshift describes the phenomenon where the light from distant celestial objects shifts toward longer wavelengths as they move away from us. This effect, known as cosmological redshift, provides valuable insights into an object's distance and velocity relative to Earth. Through detailed analysis of redshift data, scientists can infer the size, age, and evolutionary stage of galaxies observed by telescopes like the James Webb Space Telescope. However, interpreting redshift measurements requires precise calibration and an understanding of potential errors, such as gravitational lensing and instrument limitations. In addition to studying individual galaxies, astronomers are also investigating larger cosmic structures like galaxy clusters and superclusters. These vast collections of galaxies are bound together by gravity, offering insights into the large-scale distribution of matter throughout the universe. By mapping the spatial arrangement of galaxies and measuring their velocities, researchers can trace the cosmic web, a massive structure that spans the universe and defines the large-scale architecture of galaxies. The cosmic microwave background, CMB, radiation is another invaluable resource for cosmologists. Discovered by accident in 1964, the CMB represents the faint afterglow of the Big Bang. As the universe expanded and cooled, the intense heat from the early universe diminished to just a few degrees above absolute zero, leaving behind this pervasive radiation. Detailed measurements of the CMB's temperature fluctuations provide a snapshot of the universe's infancy, revealing primordial density variations that eventually gave rise to galaxies and other cosmic structures.